In the vastness of the universe, there exists an entity that defies all logic, bending every law of physics we once believed in. It is the black hole. It's not just a purely scientific concept, it's a symbol of endings, a place where all matter and light are drawn into a single direction with no way out. Every tiny discovery about black holes leaves us astonished, for they push the laws of physics to their absolute limits, where physical quantities become infinite and reality itself seems to break down. Even the great physicist Albert Einstein once doubted the existence of black holes, for it was his own equations, especially those of general relativity, that predicted the presence of a singularity at a black hole's core, a point where matter is compressed to infinite density and space-time curves infinitely. Einstein was deeply uneasy with this idea of infinity, believing that nature must have some mechanism to prevent such extreme conditions from happening. Yet, his equations kept insisting that black holes were an inevitable feature of the cosmos. But this idea had already begun to take shape long before Einstein, back in the late 18th century, when English geologist and astronomer John Michell proposed a theory based on escape velocity. He argued that if a star were massive and dense enough, its escape velocity could exceed the speed of light. He called this object a dark star. Light, the fastest thing in the universe, once trapped by it, would never escape. Over the centuries, despite tremendous progress, humanity's understanding of black holes remains shrouded in mystery. Much of what we know is still based on hypotheses awaiting confirmation. And that's why we need to uncover the truth behind what you might have completely misunderstood about this extraordinary cosmic entity. The first and most important thing: a black hole is not a physical hole. This is one of the most common misconceptions people have. It's not an empty pit or a bottomless void in space. Physically, it exists as an extremely dense sphere, a ball of matter compressed almost entirely into itself. A black hole is the final outcome of the collapse and destruction of a massive star after a supernova explosion. When a star massive enough exhausts its nuclear fuel, its core loses the ability to support itself. Gravity becomes overwhelmingly strong, crushing matter inward continuously. Nothing can resist this collapse. So why do we call it a hole? It has to do with how it warps the fabric of space and time. The black hole's enormous mass causes space-time to curve downward infinitely, forming an extreme distortion of the cosmic structure, a gravitational whirlpool into which everything slides, never to return. If we imagine space-time as a flexible sheet, then a black hole would be a bottomless depression, so deep that anything getting too close would be pulled in with no escape. In our imagination, a black hole is the ultimate destroyer, a cosmic abyss that devours everything in its path. But the truth about supermassive black holes at the centers of galaxies, such as Sagittarius A star in the heart of our Milky Way, is far more complex. They are not merely destroyers, they are also giant engines, the energetic hearts that power and sustain entire galaxies. Surrounding each black hole is an accretion disk, a glowing, superheated vortex of swirling matter. As material spirals inward, friction generates intense radiation and powerful cosmic winds. And here lies the paradox. That very energy creates a delicate feedback mechanism, a kind of galactic self-regulation system. The winds and radiation from the black hole can slow down or suppress star formation that might otherwise happen too quickly and violently. This ensures that vast reservoirs of gas and matter remain, slowly fueling the birth of new stars over billions of years. In other words, a supermassive black hole is not just a force of gravity, it's a silent architect. It keeps the galaxy balanced, neither burning out too fast from reckless star formation, nor fading too soon from lack of fuel. Black holes are the destroyers of individual stars, yet the creators of galactic longevity, guardians of cosmic equilibrium.
To form a black hole, a star must have a minimum mass at least 20 to 30 times greater than that of the Sun. Just imagine the sheer scale of such a dying star. The Sun's diameter is about 1,392,000 kilometers, while this massive star, during its stable phase, would measure 15 to 20 million kilometers across. But that's only when it's stable. In its final stage of life, the star swells into a red supergiant. The most massive of these can reach an incredible 9 billion kilometers in diameter, large enough to engulf our entire solar system all the way out to Neptune's orbit. Does a black hole reach an absolute, ultimate density of matter? The answer is no. The density of a black hole is not absolute. Let's compare densities. A single teaspoon of material from a white dwarf, the collapsed core of a star, weighs around 5 to 10 tons, an almost unimaginable weight. But compared to a neutron star, that's nothing. A teaspoon of neutron star matter weighs between hundreds of millions to over 1 billion tons, roughly equivalent to the entire Himalayan mountain range compressed into a sugar cube. All matter is made up of particles, such as quarks and leptons. No matter how small they are, they still have a fundamental spherical structure. When you pack these spheres together, no matter how tightly, you can never eliminate the tiny empty spaces between them. Thus, by definition, absolute density is impossible. Even so, we can confidently say this: within a black hole, matter reaches a density that cannot be compressed any further. A black hole represents the ultimate state of compactness, the final limit before matter collapses entirely into a singularity.
If you were to compress the entire Sun, which accounts for 99.86% of the solar system's total mass, into a black hole, it would have a diameter of only about 6 kilometers. That's smaller than the island of Manhattan. Now, let's look toward the center of our Milky Way galaxy, where the supermassive black hole Sagittarius A star resides. It lies at an astronomical distance, about 26,000 light-years away. Using the fastest spacecraft ever built by humans, the journey would take us around 40.8 million years to complete. In astronomical terms, that's nearby, but in human terms, it's far beyond anything we've ever reached. Sagittarius A star has a mass about 4.3 million times that of the Sun. When we calculate its Schwarzschild radius, its event horizon comes out to roughly 25 million kilometers in diameter, about 18 times larger than the Sun. The ruler of our entire galaxy is only 18 times wider than our Sun. Its true power doesn't lie in size, but in its unimaginable density and its extreme warping of space-time. If light can't escape, how can a black hole ever disappear? If it's the ultimate cosmic trap, does that make it immortal? The answer is no. And this was one of the greatest discoveries of the 20th century. Through brilliant mathematics, Stephen Hawking, the legendary British physicist who battled illness throughout his life, uncovered this mystery with a phenomenon now known as Hawking radiation. According to quantum physics, pairs of virtual particles constantly appear and annihilate each other in empty space. These pairs spontaneously pop in and out of existence within an incredibly short time frame, the Planck time. But something extraordinary happens at the event horizon of a black hole. Occasionally, one particle of the pair falls into the black hole, while its counterpart, the antiparticle, escapes into space with positive energy. The energy for this escaping particle comes directly from the mass of the black hole itself. This process gradually causes the black hole to lose mass over time. As the mass decreases, the event horizon shrinks. The smaller it gets, the faster the Hawking process becomes, a kind of positive feedback loop. Eventually, the black hole emits more and more radiation until, finally, it completely evaporates in a massive burst of energy. This groundbreaking discovery revealed that black holes are not eternal traps, but rather cosmic entities with their own life cycles. Black holes are the only places in the universe where time travel can be imagined in a somewhat plausible way. Because they distort space and time to infinity, scientists have proposed bold theories involving structures known as wormholes. A wormhole is a hypothetical tunnel, a bridge linking two distant points in spacetime, or even two parallel universes. Some scientists speculate that the singularity at a black hole's center might not be a bottomless pit, but rather the mouth of a wormhole, potentially leading to another universe or an entirely new region of space. This is where imagination meets physics, a frontier where daring theory and cosmic wonder intertwine. We often celebrate Albert Einstein's general theory of relativity, humanity's greatest theory of gravity. But there is one place where even this masterpiece collapses spectacularly: inside a black hole. Einstein's equations predicted the singularity, a point where all matter is crushed into an infinitely small space. However, when you try to calculate the conditions at that core, the equations yield only one answer: infinity. And infinity isn't a solution, it's a red flag, a sign that the theory itself breaks down precisely where it should be most powerful. To truly understand what happens at the heart of a black hole, we need an entirely new theory, a union of quantum mechanics and gravity. We call it quantum gravity. This isn't just another scientific puzzle. It's one of the greatest unsolved mysteries in modern physics, and perhaps the ultimate key to unlocking the final secrets of the universe. Black holes are proof that reality is stranger than any work of fiction. They mark the ultimate limit of gravity, the place where time and space themselves come to an end. And they are entities so extreme that even the greatest minds in history tremble before them. They remind us that the universe still holds secrets beyond our understanding, mysteries that our mathematical equations have yet to explain. They teach us humility in the face of nature's boundless grandeur. But here's the final truth. Even though black holes are the rulers of gravity, the most powerful force humanity has ever discovered is not a black hole. While black holes remain the densest known objects in the cosmos, the universe is filled with even more mysterious phenomena: primordial black holes, dark matter, and dark energy, forces that govern the cosmos in ways far stranger and more unfathomable than ordinary black holes. That's why physicists continue their relentless quest to search, to decode, and to understand the ultimate nature of our universe.